Hello, thank you for clicking on this link to watch this screencast, which should last about half an hour. And in this screencast, I'm going to show you some recent development we've made for the classification of 2D carbon allotropes. I'll provide you a reference on this work at the end of this presentation. And hopefully, you will find this very useful in understanding how we can do a systematic classification of two-dimensional carbon allotropes. So of course we know that carbon comes with different carbon nanostructures and structures in general come in different allotropes, and these allotropes really means that the same element carbon can assume different configuration and different structures, um, and actually many different properties as well. And we know we go from very flexible material like graphene to very hard material like diamond. We also have quantum dot, really, which is or molecule like the fluorines, carbon nanotubes, and so on and so forth. And we all know that this richness in the allotropes of carbon come from the unique uh, configurations of the valence electrons, the four valence electrons in carbon. And it comes from the fact that, roughly speaking, those four valence electrons can add a 2s and a 2p orbitals. And those are close enough in energy that they can hybridize to create a range of bonding types. So we know the sp bonding type, which is actually seen mostly in molecule, but also in one-dimensional chain of carbon. They correspond to triple bond, and it's actually lead to carbon to only bind to two different atoms or two atoms. We have the sp3 bonding, where all three p orbitals hybridize with the s orbitals to yield four equivalent orbitals, sp3 orbitals, and because they're equivalent, they arrange on the tetrahedron, and this is the basis of diamond, for example, but also of molecule like CH4. And finally, we have the sp2 hybridization, and this hybridization involves two p orbitals hybridizing with the s orbital, so leading to three orbitals, which are shown in blue on the top right pictures on this slide. And then there is the remaining p orbital, which is perpendicular to the plane, formed by the three sp2 hybridized uh, orbitals. Now, what's interesting with this is that, of course, the orbital sp2 being in their plane, they they are they are at an equal angle, and the angle has to be 120 degrees. So you form a double bond like this, a sigma bond coming from the sp2 orbitals overlapping, and then the additional bond, which is a pi bond, come from the gray orbital, the p orbital that's left after hybridization. So what's good about this is that by geometry, by geometrical constraint, the bonding the blue bonding that we see in this picture takes place at 120 degrees, which is exactly the right angle for an hexagonal network. And one of the reasons why it's so exciting is because 120 degrees hexagonal network correspond to a closed pack system, which we see in nature very much, because closed packed is seen in nature as a minimization of energy. So of course, nature has known that for a long time. This is a typical picture of a honeybee comb. This is what they do for in in the hives. And we know that this is like this because of the close packed nature of of uh, of the construction, and this is what evolution led to. So it's an optimal solution for a given environment. But if we look carefully in different honeycomb like this, we see that even though they are mostly hexagonal, we see there are things that are not exactly hexagonal. For example, if we look here, there's a square right there. Right there, there's a pentagon. Even find some heptagons. And in fact, we see all sort of other rings in here. And it's also always interesting to look for images like this where everything should be hexagonal, but it turns out there are some non-hexagonal rings. And these have a very important effect on the overall geometry of the system. As we know, very often defects is what makes things interesting. And this is what people have been thinking about when they think about sp2 carbon and sp2 carbon allotropes. So that's very exciting. I mean, we all know about graphene, but here on the next couple of minutes, I'm going to show you 45 structures that have been studied by different groups over the past 20 plus years. And these structures have been studied either theoretically or experimentally, and they are all crystalline. They're all two-dimensional crystals. You will see in the picture I'm going to show you, each time the blue box will show the primitive unit cell. But one thing I like to attract your attention on is when you watch this, please pay attention to the caption. In the caption, this is the name that the original authors gave to the structure. And so you will see that there is a richness in those names, but frankly, it has now come completely out of hand in the sense that it's very difficult to classify the structures based on their name. So let's go for it. So this is graphene. This one is no problem. C312, azographene, T-graphene, B4-graphene, biphenylene, CMMM568, which really is the space group that we have, chorographene, D4-graphene, and so on and so forth. I'm not going to say all of them. But all these structures that I'm actually going through right now have been studied in the literature over the past few years. And if you look at the names, it goes all over the place. It's extremely difficult to search the literature to understand what is what and what are the properties that we have. So, for example, here NetY, this one is one of the original structures, 0567. We have octite, we have OPGZ, and so on and so forth. So all sort of things that we have, and their name is really not indicative of anything about the properties. So this is not really helpful. All those studies assign names that made sense for that study itself, but not in this very rich area of research. And so I'll keep going here. And so you see those structures with very large pores that could be used for energy storage or things like this. But there is no way knowing from the name that it's a structure like this. We have other more compact structures like this. I'm showing them all to you now just because I think it's important to realize the zoo of structures that we have. As I said, we found 45 as of a couple of months ago. And of course, I'm going quickly in them. So the reason for this presentation here is to explain to you what we have in mind about characterizing those structures, finding a way to systematically name them, search them, and cataloging them. And of course, you know, here you have structures that are defined by polygons and structures like this. So it makes very quickly sense to look at the topological properties, and people who are familiar with some elementary geometry would think directly that what makes sense to look at is the Euler characteristic. So the Euler characteristics of these different structures could be a good way to start in our journey to find a way to catalog those structures. So the Euler characteristic, and just reminding you, is a topological invariant that describes a surface. Okay, and it's topological in the sense that property does not change if you continuously deform or bend the structure. So if you don't create holes or tear or anything like this in the structure, you keep this topological characteristic. It's usually written chi. And the important equation is the one in the yellow box. It says that the number of faces, so number of polygons, right? We have polygon, number of faces minus the number of edges plus the number of vertices is a constant, which is a topological constant chi. So when you go on Wikipedia, you see this interesting, well-known table here that shows a number of polyhedron and with a number of vertices, edges, faces. And you see that if you indeed look at F minus E plus V, or the other way around, it's fine. I mean, or the opposite. You see that, I mean, not the opposite, I'm just saying that in the table, V and F are introverted, but it makes no difference. And so you see that the V minus E plus F is indeed a constant. And this constant is really the fact that all those polyhedron are topologically equivalent. So if you were to replace those polyhedron by some kind of clay, and you can deform the clay in different shapes, but it's topologically you're not creating any tears or holes, and so that's why they're equivalent. Now, what's interesting is the Euler characteristics, and there is a very interesting body of work that's available relating to connecting this characteristic to the curvature of the surface, the Gaussian curvature, which is itself topological invariant using the Gauss-Bonnet theorem. But really what matters is the fact that this Euler characteristic is directly related to another characteristic of the surface, which is called the genus G of the surface. And it's very interesting to see that there is a very simple relationship between chi and G is the number of holes in the structure. So the best way to see this is to look at an example. So a series of examples really on the pictures on the left. And you see that G is exactly the number of holes. You have 1 hole in a donut, 2 holes in a double donut, 0 holes in a sphere. So the genus of a sphere is 0. And of course, if the genus of a sphere is 0, that means that the Euler characteristic is 2, exactly as we found for the polyhedron. Okay, so I spent a couple of minutes on this because this is very important to the following our following quest to try to understand these structures. So now let's go back to the problem of sp2 nanostructures. What does that mean, sp2 nanostructures? It means that every single atom is connected to exactly 3 other atoms. That's really the condition. And so what we are trying to do on this slide here is to see how this Euler criterion, that Euler equation that we have on this slide, can be rewritten for structures that have a threefold connectivity, as we are interested in here. First of all, well, you just said that chi is equal to 2, 1 minus g, so let's do this. So again, f is the number of faces, e is the number of edges, and v is the number of vertices. So if we go back to material science or chemistry, the number of edges is really the number of bonds, the number of vertices is the number of atoms, and number of faces is the number of rings that I showed you before. So how do we translate the fact that a threefold symmetry, threefold connectivity, is related to this equation? It's actually easy to convince yourself that this is the case. These 2/3 come from the fact that each vertex, so each atom, has 3 neighbors, okay? So creates 3 bonds, but each of these bonds count as 1/2 since it is shared with another vertex. So this is the interest of having a recorded screencast. If you have any trouble with this, pause, make a little sketch on a piece of paper, and you will see it directly. We can also relate the number of edges, or again, number of bonds, with the size of the different rings. So here I introduce a new notation, alpha I. Alpha I is the number of rings that contains I edges. So we have this sum of I alpha I. We need 1/2 because, of course, we do a double counting, right? Because every single ring neighbors another ring. So if we count every single, if we would be counting the number of edges twice, because an edge is part of 2 rings. And finally, the number of rings, total number of rings, or the number of faces, is of course the sum of the number of rings with I sides. So when we put all this together, we find this interesting equation, which is actually true for every sp2 carbon nanostructures. This is a very well-known equation. It's not a finding of this work, of course, but it's very useful. Usually we like to remind people that this explains why fluorine have 12 pentagons. You can see that. You can also see that in sp2 carbon, adding hexagons does not change the topology. Indeed, each time you add an hexagon, so in other words, when you increase alpha I, this does not contribute to the sum because you have 6 minus I. So for I equals 6, you can have any alpha I you want. That's also the reason why you can grow a carbon nanostructures, an sp2 carbon nanostructure, by adding hexagon and hexagon without changing the shape of the system. But if you want to change the shape of the structure, you need to add defects like pentagon, heptagons, and so on and so forth. But we actually can even simplify this further. There's a tiny subtlety, but we are going to look at it now. We are looking here at two-dimensional systems. Two-dimensional system means that you have a periodicity in two directions. Topologically speaking, periodicity in two directions is equivalent of saying that the periodic boundary conditions are that of a torus. So you have in one direction of the torus, you have one of the dimension. In the other direction of the torus, you have the other dimension. So this is the equivalence of the fact that we have a two-dimensional, exactly two-dimensional tiling of the space. Now, if it's equivalent to a torus, that means that the structure itself has one hole, so G equal 1, and therefore the equation simplifies even further to this equation. So now, the reason why I spend a little bit of time on this is because what's interesting about it now is that this equation basically says that the average size of the rings is 6. Right? That's exactly what it means here. This is a sum of the average size of the ring is exactly 6. So that means that there is something going on with the rings that we have in our structure. So let's have a look at a few of the structures I showed you before. I'm just going to show you about a dozen of them, not going to go back to the 45, but that's not necessary. So let's go back with this in mind, that the average size of the ring is 6. Well, if we look at graphene, of course, we have only one hexagon per unit cell, so of course the average is 6. If we look at this interesting one, we see that we have triangles, but we also have this very large structure here, which is 12 atoms. So 12 atoms and 2 triangles. The average is indeed 6. If we look at this one, we have a square and octagon, so the average is indeed 6. This one is a little bit more, but the advantage is the green shape, which are hexagon, do not count, right? So we see that we have 3 pentagons and 3 heptagons, so the average is indeed 6. And you keep going and so on and so forth. So you see here, again, last one I'm going to describe in detail, 2 pentagon and 1 octagon, the average size is 6. And we can keep going. But what's important is in each of these structures, the structures seem to be really determined by the polygon content. So that's what we have, and then we have more and more complicated ones, but all of them here are clearly defined by the polygon content. So when we were trying to make sense of all this zoo of structures, we decided to base the naming scheme on the number of polygons of each type. And frankly, we tried different ways of doing this, and we were hoping that the classification that we propose would be unique so that it's actually useful. So the name that we came up with is here the classification scheme. We're going to call these structures lambda graphene, where lambda is given by this formula here in yellow. First, there is an index X, which I'm going to explain to you in a minute. It describes the type of lattice we have. And after that, we have a concatenation of rings of size n with a superscript which tells you how many of each you have. So please do not worry too much if you didn't follow my description here. This is much better explained in examples, and I'm going to do that for the next few minutes. So please do not just disconnect at this point because it seems weird. It's not going to be weird when we have examples. So before I go there, though, I'm going to explain the X. Since we are in 2 dimensions, we have wallpaper groups, so 2-dimensional lattices. We know there are only 17 of them. But there are only 5 types of lattice. So as we know, we have hexagonal, tetragonal, centered, and so on and so forth. And so for all that, this is what we use for the name X. It turns out that we find that adding this to the classification allows to better determine the type of structures we have. So this is for the X value, and you will see the X. I'm going to comment on that. But let's go back to the naming scheme and let's try it. So I picked 5 structures here that come from the list I showed you before. And this first structure here, in the first on the left, we see is a centered structure in the lattice type. There's going to be a C. We have 2 pentagons, so it's going to be 5 to the power 2. Then 4 hexagons, so it's going to be 6 to the power 4. And then we have 1 octagon, so it's going to be 8 to the power 1. So this is the name we came up with. So 2 pentagon, 4 hexagon, and 1 octagon. The next structure, graphene, it's hexagonal, so it's going to be H. And there's only 1 hexagon, so it's going to be H61. So H61 is graphene. Biphenylene is going to be, this is a rectangular cell. We have a square, a hexagon, and octagon, so 4, 1, 6, 1, 8, 1. Fagraphene, which is a little bit bigger, has 2 pentagons. It's a rectangular system. It has 2 pentagon, 6 hexagon, and 2 heptagons. And this is what we have. And finally, pentaheptide has 4 pentagon and 4 heptagon, and it's also a rectangular system. So it's like this. So these names seem to make sense, and in fact, they are pretty systematic. And on top of that, they provide you a lot of information. For example, they give you the number of rings. The number of rings is just the sum of all the superscript. So we have 7 rings, for example. And of course, if we each ring is basically defined by 2 atoms. Okay, you can find that easily from the slide I showed you when we derived the Euler characteristic equation for the sp2 carbon. So we have 14 atoms in the cell. The number of rings for graphene is 1. Number of rings for biphenylene is 3. Then we have 10, 8. And of course, the number of atoms can also be found. So you see from this very simple classification now, we find that we have a unique name. We have names that are pretty clear, describe the structure, tell you how many atoms you have, and so on. So it's pretty useful classification. Now, it's only useful if it's unique, or at least if it provides an unambiguous description of the lattices. So the next slide is not a slide that usually we show in a presentation, but I'm going to show it very quickly so to convince you. It's come from the recent paper we just published on this topic. And the first column are all the names of the 45 structures that have been reported. And the second column are the names that using the scheme I just presented to you. And in fact, I'm not going to go in details in this slide. Instead, I'm going to show you something visual in a second. But the point is, in all the structures that have been done experimentally, not experimentally necessarily, but in the literature so far, they will have a unique symbol, as we said. So just to give you an idea, here are some of the structures among the 45. Very colorful, very busy slide, but it's an important one because we describe all of them. So just to go back in specific examples, this one here, see a little bit more complicated. It has a 12-member ring, it has 6 pentagon, and it has 3 hexagons in the unit cell. Again, in the primitive unit cell, so hence the name. Let's have a look at this structure, which is also a lot of large pores. So this one is really complicated name, but the name itself, the symbol we come up with, it's pretty compact, in fact, and it tells you what's in there. What's even more interesting is that you can actually find those names in a systematic way if you do high throughput calculations. Just for completeness, here are the rest of the 45 structures that have been studied experimentally, and they are all here. And if you're interested in looking more in detail, I invite you to pause this screencast and look at them. Now, I have to say that we were very pleased to see that our classification scheme yielded unique names in everything that has been studied in the literature, which was our goal. Now, of course, we always want to go beyond, and then we decided to try to see, Okay, what about structures that have not been studied yet? Are they also going to have unique names? And for that, we had to develop algorithms to find to find new structures. And in fact, we did, or in fact, my student did, and we actually found one example of a structure, of a crystalline structure that has the same symbol but have two different structures. So we found this one here, and we also find that these are pretty rare situations, but we wanted to expand the notation for those rare situations, again, with this idea of high throughput and classification in mind, right? Just to being able to classify. So these two structures here have the same lattice type. It's just a centered lattice type. They have two heptagon, two pentagon, two hexagon, and one octagon. So what we decided to do is to say the difference between the two is that the local environment around each ring is different. So what we decided to do is to expand the notation for these cases, where we start from, we provide the local environment to the ring starting from the smallest one. So again, let me explain to you by the example. So the way we do this is the notation that's written on the top. And we come up with a string S, and it corresponds as a subscript, correspond to, for example, one of the pentagon. And for that, the neighboring of that pentagon here, the top yellow one, is as one hexagon, two hexagon, three hexagon, one octagon, and a second octagon. So in other words, the local environment along this pentagon is three hexagon and two octagon. Now, if we look at the other system, we find that the neighboring rings of the top pentagon is one pentagon, one octagon, one hexagon, two hexagon, and then one octagon. In other words, the neighboring rings of the pentagons are another pentagon, two hexagon, and two octagons. So when we expand these names like this, we see that they are become unique. It can become a little cumbersome. However, it's systematic. So there is a systematic rule to do so. And that means that you can actually identify the structure uniquely, which is exactly the idea. Now, there is another situation where you have something similar. And the other situation is when you have defects. Now, people have been studying defect for many years and for actually decades. The question you can ask yourself is that the structure I showed you here I'll show you on the screen, are they really crystalline structure or periodic for really the convenience of the calculation? Well, usually we put defects in structures and we put them far away from its image so that we can study the properties of the defect themselves. But still, these structures are periodic, and even though they can seen as a defect embedded in a regular graphene in this case, they do constitute crystals. And these two examples I showed you here, actually it's a 5775 defect. You can see that at the origin of the blue arrows, for example. And in the two unit cell I show you here, the two unit cells have exactly the same number of rings of each type. And the local environment to each of them is also equivalent. Again, this is because of the embedded system. So this is where we expanded the notation, which is actually probably very useful because the name, again, is not simple, but it's systematic. It can be calculated very easily. And then let me explain to you the naming scheme that we have under each slide, under each picture. So the defect is a 5272 defect. It's a defect, so we have the letter D that start. Then we have the at, which means that the defect is embedded into H61, which is graphene, and it is embedded there at the position, the lattice position 444 minus 3, and you can see that according to the lattice vectors I give on the plot. And then the other structures that differ from the first one by the positions of the defect. So this is actually, again, in terms of metadata that described uniquely the defective structure. So once again, for high throughput or systematic studies, it's exactly what we need. Now, I'm pretty much done with the classification, but we learn a lot of things through this work, especially when it comes to naming, when it comes to building the structure. So I would like to complete this presentation in the next 5 minutes or so with two questions. The question is the Euler's rule a sufficient tiling condition? In other words, if we find a configuration of rings that obeys Euler's rule, does that mean that the tiling situation exists? And the second one is that can we generate all possible tilings that obey Euler's rule? So when I say possible, I mean those that obey Euler's rule but are also tiling solution. And the answer to the first question is no, Euler's rule is not sufficient. And the second equation is that if it is, once we have the sufficient tiling condition, we can indeed build them. So first, let me try to prove that Euler's rule is not sufficient. The advantage, of course, is for proving that something is false, I just have to find a counterexample. That's exactly what I'm going to do. So let's remind what the Euler's rule. Euler's rule is this. Basically says, or Euler's criterion is that the average size of the ring is 6. And let me remind you also that the sum of alpha n being the number of rings of size n, is big N being the number of the total number of rings. All right. So you can, just looking at this with forgetting a little bit about our sp2 tiling and so on and so forth, we can actually find the solution to this, how many solutions to the equation there are. This is an interesting problem in number theory, and the solution is actually given by this equation where pi is the prime counting function. And so you can find a number of solutions to this equation. And in fact, the plot is like this. We see that the number of solutions increases like this. Okay. Now, let's have a look. Let's start to see if the number of these number 1, 4, 12, 34, 84, 199 are indeed tiling solution. We know they are solution to the Euler criterion equation, but are they also tiling equation? And hopefully we won't have to go too far to prove that that is not correct. This is not true. So first of all, let's look here the first time. So one polygon. One polygon means that we have, this is true, the one polygon, the sum of alpha n is equal to 1. So we have one polygon. At the same time, the average size of the polygon is to be 6. One polygon and the average size to be 6. Obviously, the answer is that we need to have alpha. Only one alpha is non-zero. This is alpha 6, which is equal to 1. In other words, we have one hexagon. Well, this is graphene that we've already seen. So this is an interesting thing to think about. If you have two atoms, so one ring or two atoms in one unit cell, if you have an sp2 bonding, the only way to do it is through graphene. Now it becomes more interesting when you have two polygons. So you have two polygons, and again, remember, two polygons, and we need to find two polygons whose average size is 6. Well, as you know, the smallest polygon you can have is a triangle. You cannot go lower than that. So that means that the combination of two polygons with an average of 6 are given in this table here, 3, 9, 4, 8, 5, 7, and of course 6, 6. Now, we studied these structures in our search algorithm, and 3, 9 actually is this one. It's a hexagonal system, 3, 1, 9, 1 in our naming scheme. 4, 8 is this one. It's also the primitive cell. It's a tetragonal one, 4, 1, 8, 1. And 6 is obviously graphene. You'll notice that in the last plot, I plotted H61 because we always have to name according to the primitive cell. Now the 5, 7 is not actually possible. a unit cell with just 1, 5, and 1, 7 in the unit cell is not possible. And the reason for that is because it corresponds to a dislocation. In fact, it corresponds to a grain boundary, which incidentally we observed with my colleagues more than 20 years ago in STM images. So in fact, these STM images show that in 2 dimension, if you have 5 and 7, you're actually creating a dislocation. And if you create a dislocation, that means that you cannot make a crystalline system here, so a periodic system, with just one dislocation. I also invite you to read this paper here 25 years ago, which is actually an interesting paper talking about dislocation in SP2 systems. I'd like to attract your attention to the fact that 5, 7, 1, 5, and 1, 7 in unit cell is not possible, but of course we can have more than one. And in fact, I already showed you these results. We can have 2 5s and 2 7s, and then that we end up with a C5272, but this is a different situation. We have 4 polygons instead of 2 here. And also for those who are interested in dislocation theory, that's because the 2 Burgers vector, the 5-7 pair correspond to a Burgers vector. If you put 2 of them, you can put the Burgers vector in such a way that they cancel each other. They sum to 0. Now, in this process of creating the structure, so clearly that proved the fact that it's not because a pair or a configuration obeys Euler's rule that it's going to be a tiling solution. That was answering this question. Now, can we create all the tiling solutions? The answer is yes, and I will probably provide another screencast about that, but just let me give you a little bit of hints of what we've done here. So we've demonstrated this. There are 3 graphs here. The one in gray-blue is the Euler's condition. The next one are the possibility. So the greenish one is the possibilities. You see the number 3 there correspond to the fact that the 5, 7 is not possible. But if we consider degeneracies, so 2 structures that have the same rings number but with different configuration, then we end up with numbers that increase dramatically. And I have to say that most of those that increase come from the presence of triangle, because there are many ways to put triangles. We know triangles are not necessarily expected in organic chemistry, but from a geometrical standpoint, they are perfectly valid polygon. Now, let me show you an example of what our search algorithm provides. For example, with 8 atoms, so 4 polygons. And here I do not show any of the system with triangles. And then we found, this search algorithm found all those 9 structures. Some of them were known before, some of them were not known before. And to our pleasure, I would say, we find, to our not surprise, but we were satisfied that even those structures, they all correspond to a naming scheme that's unique. So again, the naming scheme proved to be useful in this instance. So I think that it's time for me to wrap up this presentation. Just telling you that we have this naming scheme for graphene with defects, and they create crystals, and we have a unique naming scheme that's actually very well adapted to studying defective structures as well. And if you want to learn more, we just published this paper in the journal Carbon. It's already available online. I have to say, I have to give credit to the people who did the work here. Eduardo, so Edu Costa Giran, professor in Piauí in Brazil, came up with the original idea, the initial idea. Alastair, undergraduate student who did actually all the search algorithm, it's something of very nice. And my role there as a cheerleader, I suppose. So we did this work, and I hope that it was of use to you, and I will be happy to answer any question if you want to. One last thing I'd like to mention is that all the structures I showed you today in this presentation are available for download. It's one of the reference that's in the paper there. It's going to lead you to a repository that's freely available, and I invite you to use them. Thank you very much.